So good morning. My name is Junkyo Jung, a PhD student at Yonsei University. And I'm very honored to be the first speaker of the day. And I'm here to present our work, Moneta Ex-Vivo GPU driver fuzzing by recalling in-vivo execution states. And this is a joint work with my collaborators from Yonsei University, KU Leuven, and TU Delft. So these days, we all know that GPUs are core to AI computing, but the problem is that the GPU drivers are still very vulnerable. So for example, NVIDIA assigned 27 GPU driver CVEs with high severity last year. So to find driver vulnerabilities, fuzzing is a good method, but there are two big and well-known device driver fuzzing challenges that prior works have tackled. First is the inter-syscall dependency challenge, where syscalls have to satisfy both value and ordering dependency between each other. And the second is the hardware dependency challenge, where the fuzzer must somehow handle the I/O operations coming from the GPU driver. So an easy way to do this would be to use an actual device, which is an in-vivo approach. So an in-vivo approach is where the actual device exists during fuzzing to handle driver I/O requests. So for example, a prior work runs fuzzing on a virtual machine while I/O requests are handled by the actual hardware. There are advantages to using actual hardware, but the problem is that the fuzzer would require an actual device for every single fuzzing instance. So to solve this scaling issue, researchers have also proposed Ex-Vivo approaches. So on Ex-Vivo approaches where the actual device does not exist during fuzzing, there were multiple Ex-Vivo works that tried to tackle this challenge. First one is hardware access evasion by stubbing I/O functions. And the second is static analysis methods, such as using symbolic I/O to generate an input that does not require a hardware. And lastly, record and replay by using a recording-based emulated GPU. So using record and replay actually is quite promising because it can also mitigate the first challenge. And dependency between syscalls can be mitigated because recordings generated from workloads are already in dependency-satisfying formats. However, a problem in record and replay is that deterministic record and replay requires recording and replaying all external and non-deterministic events. And for example, this could be concurrency in multiple threads and timings between syscalls and device-side interrupts. And recording all of these could degrade fuzzing speed. So an existing approach to mitigating non-determinism is by using snapshots. And by recalling desired driver states from snapshots, we can mitigate the non-determinism problems. And by using snapshots, we can also address the device-side input challenge. So for example, if an I/O request is required to reach a deep state in the device driver, we can simply use a normal GPU workload to drive the driver into a deep state. And then we take a snapshot of the state and rehost the snapshot to start fuzzing from the state. So from these approaches, our insight was that we can combine snapshots and record and replay to complement each approaches. So now let me quickly go over Moneta's design and the challenges that we have tackled. So the core idea of Moneta is simple. We use a GPU workload to drive the driver into a deep state, and we take a snapshot in the certain deep state, and we rehost the snapshot onto a fuzzing machine, and we transform the previous GPU process into a fuzzer by what we call fuzzer implantation, which I will go over later. So now in the fuzzing machine, the GPU driver is previously snapshotted deep state, and the GPU process is replaced with our fuzzer. And now we add record and replay. So during the snapshotting phase, we also do what we call post-snapshot recordings, and this is literally recordings of syscalls after we take the snapshot. And on the implanted fuzzer, we replay the recordings, and we mutate these post-snapshot recordings to find bugs in deep driver states. So this is the simple but core idea of Moneta. Combination of snapshots and record and replay deterministically recalls deep driver states while still allowing the fuzzer to be capable of evolutionary fuzzing. Now let's go over some key techniques that were used to implement Moneta. So the key in rehosting was how we transformed the GPU process into the fuzzer on the fuzzing phase. And this has to happen without destroying the driver internal context. So in order to do that, we use what we call Moneta agent. And what this mainly does is to monitor the GPU process. So to implant the fuzzer on rehosting, the first syscall from the GPU process is intercepted by the agent. And the agent manipulates the syscall arguments to force the GPU process to execute the fuzzer. Now the GPU process is executed into the fuzzer, and the fuzzer can keep the same PID as the previous workload. So using this Ex-Vivo approach is quite important because what we observed was that most GPU drivers contain process ID checks. For example, this is observed from the NVIDIA driver, and this PID check is called during mmap in NVIDIA GPU's driver. So, and another thing was that it was also important to preserve the device file descriptors in the GPU process. We observed that most device files in workloads were opened with close on exec flags. And this means that if we just proceed with the Ex-Vivo fuzzer implementation, naturally we will lose all of these active device file descriptors. So during the snapshotting phase, when executing the workload, Moneta agent also intercepts all device file open calls. And then the agent erases the close on exec flags prior to executing the open call. And this allowed us to stop the file descriptors from closing when we execute. So in the end, these two techniques allowed the fuzzer to operate with the same PID as the original GPU process and also easily preserve the file descriptors in the GPU workload. So our fuzzer implementation techniques allowed to preserve live driver internal context for Moneta's stateful fuzzing. So what we also aimed to do was to make our system a practical GPU driver fuzzer, and by practical, we wanted Moneta to be able to fuzz all mainstream GPUs, including both discrete and integrated GPUs. So for discrete GPUs, snapshot and rehost is easy because we just rehost the KVM-enabled x86 machine onto the same KVM-enabled x86 machine. However, for integrated GPUs on ARM, the emulated ARM's vCPU was not up to date with the actual ARM CPUs, and this made rehosting fail. Precisely, rehosting failed because of the CPU feature differences between the snapshotting and fuzzing environments. So what we did was to disable these unmatching guest CPU features in the hypervisor level, and this allowed the vCPUs in both states to contain the same CPU features and made it possible to rehost the KVM-enabled virtual machine onto an x86 machine with an emulated ARM CPU. And this technique allowed Moneta to fuzz all mainstream GPUs, including both discrete and integrated GPUs. And now, before we go into evaluation, I'll briefly go over our experimental configs. We implemented Moneta on QEMU with Linux KVM on both x86 and ARM. And we tested NVIDIA GPUs with 3 different architectures and 1 each for AMD and Mali. And these are our main basic block coverage results from fuzzing the GPU drivers from the left, NVIDIA, AMD, and ARM Mali. So since Moneta's key contribution is combining snapshots and record and replay, we create 2 strong baselines to show their effects. The first baseline, number 2 and blue, removes the snapshotting from Moneta and simulates a typical record and replay fuzzer. And the second baseline, number 3 and green, removes both snapshotting and record and replay from Moneta. And this simulates a typical syscaller use case without a starting corpus. So number 1 and red is fully configured Moneta. So on fuzzing NVIDIA drivers where Moneta was the most effective, Moneta's coverage increase was about 130% compared to our no snapshot and replay baseline. And in all drivers, advantage of Moneta is clearly visible. And what we also did was a few ablation studies, and I'm going to introduce one of them, which is we call no FD config. And this configuration has the same snapshot and record and replay capabilities of Moneta, minus the file descriptor preservation I explained before. And the difference in coverage shows that our FD preservation is critical to preserving driver internal context. And by Moneta, we found and reported 10 previously unknown bugs in 3 drivers, where 5 were assigned to CVEs. And we also measured how Moneta performed in terms of throughput. And so for native x86 instances for NVIDIA and AMD, were able to execute about 20 to 30,000 programs per minute. And emulated ARM performed reasonably with about 2,000 executions per minute. And in the paper, we also present other ablation studies, rehosting techniques, and comparison to previous GPU driver fuzzing works. So wrapping up, we combine snapshots and record and replay to design an Ex-Vivo fuzzing system that deterministically recalls deep driver states while still being capable of evolutionary fuzzing. And we also open sourced this system, Moneta, which brought maximum 137.8% increase in block coverage compared to state-of-the-art fuzzers, and found 10 previously unknown bugs with 5 CVEs assigned. So thank you for listening, and I am happy to take any questions.
Thanks for the talk. And anyone has a talk, has a question, I invite them to step up. All right. So actually, I have a couple of questions. I find your approach very interesting, where you combine snapshotting and replay. Could you elaborate a little bit? What is your approach to get the initial snapshots? So how do you decide what snapshot is worthy for the fuzzing session later? And how do you collect the data?
Do you mean how we chose where we take the snapshots?
Yeah. How do you, in general, how that part works?
Actually, we chose the snapshot points heuristically. Like, for example, if we run a workload previously and we count the number of IOTOs inside the workload, and we just divided the snapshots equally between with equal intervals. So where we take the snapshots wasn't our scope of the research.
All right. And I have another question, which is related with the second part, when you fuzz the input, where the device then is emulated, if I understood correctly. Can that generate a false positive because maybe the emulation is not faithful and you have a crash that is not be reproducible somehow?
Yes, since we use emulated GPU on rehosting, it is possible that there were false positives, but what we encountered wasn't, we did not encounter any false positives, and we tested all the bugs with the real GPU, and we made a testing program with the same bug triggering traces, and we tested that even with the real GPUs, all the bugs were triggered.
Okay, thank you. Thanks for another round of applause for our speaker.